Hi, everyone. My name is Andie Migden, and I am a senior GIS analyst at RIPCO Real Estate. And today, I will be presenting to you all on how to predict rent prices of ground floor retail real estate using geographically weighted regression and spatial regression. So RIPCO Real Estate is a retail-focused commercial real estate firm with 6 offices in the tri-state region and two newer offices in the Florida markets. We provide a variety of services such as tenant representation, landlord representation, investment sales, among others. And we are a rapidly growing firm in terms of our brokerage, but also in terms of our GIS department. RIPCO has had GIS for around 5 years. However, within that short time, we've built a unique platform of capabilities and have created a collaborative space for the team to come up with creative, actionable, and impactful ideas. And this very presentation is one of those ideas that you'll see today. So, when I say rent prices, I'm talking about the rent prices of ground floor retail real estate space in price per square foot. So how is this determined? If you were to walk into my office and ask any of the brokers this question, you would get a variety of answers, such as the lovely neighborhood appeal, or the rent of surrounding similar properties that were recently leased, or the amenities within the property, such as the square footage, a new HVAC system, the presence of ventilation, among others, as well as the amenities outside of the property, such as proximity to transit, as well as the mix of retailers in the area, known as the co-tenancy. So all of these predictors that go into rent are spatial, and that's why we're here today. Now, GWR, geographically weighted regression, applied to real estate is actually nothing new, so you're probably wondering maybe why are we here? GWR is far less studied in terms of retail commercial real estate. So this presentation will walk you through those unique predictors that go into rent prediction. And in the second half of the presentation, I will walk you through an optimization strategy that uses RStudio code to automate the entire process of parameter exploration as well as the optimal model selection. So it would be hard to describe Manhattan with just a few statistics. Daytime population density is a little over 140,000 people per square mile. Median household income is a little less than $90,000. An average assessed land value is around 1.3 million. But what does this mean exactly? The story falls short with any more granular details, and statistics aggregated to the Manhattan scale are global. So in the absence of any other information, it's assumed that these high-level statistics are representative of the entirety of Manhattan. Of course, that's not true. If you were to use traditional multivariate regression, you would be calibrating this model using all the features in your study area. That would mean there's one model to describe Manhattan and one model to predict price. And you can't tell a full story with just a simple broad strokes average. Manhattan's full story lies within its beautiful neighborhoods. So a neighborhood can be seen or noticed by a socio-demographic commonality, or perhaps a landmark or park, museum that's prevalent in the area, or also the mix of retailers that define the neighborhood. Times Square, which is very big box heavy, looks a lot different than Chinatown, which has way more mom and pop focused shops. And most importantly, how do all of these factors affect real estate price, rent prices? So using traditional multivariate regression, it's well assumed that our independent variables, our predictors, are in fact independent. However, our neighborhood characteristics clearly depend on location. And looking at the maps that you see on the right-hand side, you can see hot spots and cold spots indicating clustering of spatial autocorrelation. And we need a model that deals with these spatial effects. Otherwise, rent prediction will be over or under priced. So we need a model that deals with both the spatial autocorrelation, our spatial clustering, as well as the spatial variance of our predictors that exist throughout Manhattan, our spatial heterogeneity. Geographically weighted regression incorporates these local spatial relationships into what was a formerly global model had you used a traditional regression model. GWR explores the spatial variation of these predictors throughout Manhattan. In traditional OLS, you would calibrate one model using all the features in your study. Using GWR, each point, each feature, gets its own equation, and that equation is calibrated using only the data from its nearest neighbors. Looking at the visual here on the map, this shows a GWR model that optimized an 89 neighbor bandwidth, meaning that each point is calibrated with a model that incorporates only its nearest 89 neighbors. So, if each point has its own regression equation, each point has its own local coefficients and its own local statistics. If you had used a traditional multivariate regression, these coefficients would be the exact same throughout Manhattan. And as you can see, there's so much visibility here. Looking at co-tenancy diversity, for an example, this statistic, this variable, can explain price a lot more in the Soho region, which is bright red, than it can in the cooler areas of Manhattan, such as Midtown and Murray Hill. However, if each point has its own equation, in my case, that was over 2,500 equations, and I needed a way to simplify this. With each feature's equation, there's also an R-squared value. And each R-squared value combined creates a neighborhood, similarly. So here we can see that the 2,500 point-specific equations are now reduced to 7, indicative by the 7 neighborhoods that you see here. So, of course, the maroon is neighborhood 1 with the highest R-squared value, red is neighborhood 2, and orange is neighborhood 3, and so on. No longer is the Upper East Side just the Upper East Side, but rather Madison Avenue from 59th Street to 70th, from 59th Street to 70th Street, the Lower East Side, the East Village, anywhere that's maroon, is considered one neighborhood. So when I say neighborhood, I'm no longer talking about Soho or Times Square, but these are derived clusterings of similar point R-squared values. So the whole point of using GWR is to create these regionalizations. And it's within these regions that the combined variables effect on price doesn't change, no matter where a space is within that neighborhood. Therefore, we're trying to solve the problem of spatial autocorrelation, of spatial heterogeneity, by making these regionalizations. And once you have your neighborhood data subsets parsed out, then you run 3 regression models on each data subset. Multivariate regression, as you've seen before, it's aspatial, and then spatial error as well as spatial lag. At a high level, one of these 3 models will be ideal for each neighborhood. Multivariate regression does not deal with any spatial effects, and it estimates a single error term. The spatial error model deals with the spatial effects in the error term. It takes our original error term and splits it up into random error and spatially structured error. Our spatially structured error is composed of our spatial error coefficient, lambda, and our original error term multiplied by a spatial weights matrix. You can see here we're dealing with spatial effects in the error term. Similarly, the spatial lag model instead deals with those spatial effects in the predictor variables. Congratulations! You can all now predict rent better than a licensed broker. You have the tools to do this. There's just one small problem. With countless variables and variations of those variables, how would you know which ones to include in your model? Also, as the data changes over time, how does the importance of each predictor variable change? How do these data-derived R-squared regionalizations change? In the second half of this presentation, using RStudio, I've created an optimization strategy that explores all model parameters and automates the entire process to get to your final neighborhood models. So these 4 steps outline exactly what I just walked you through in the previous slides, with the difference of this code will run through those dozens or even hundreds of combinations to get to what's best for your neighborhood. So let's take a closer look at the logic behind the code. First step, prep the data and run GWR. You have to make sure that none of your variables are multi-collinear with each other. So the code creates a table that does just that. It creates all the possible combinations of variables to put in each model, and that table gets fed into a flexible GWR function that employs some of the functions that exist in the GW model spatial package. Second step is to save the results and select the optimal model. So after each run, the code does 2 things. First, it automatically adds the results to the table of each GWR model run, and it also saves those enriched points containing the GWR local statistics. So this is essentially a back and forth ping-pong effect between the GWR function, adding the results to this table, and saving your points that have the enriched data. Seamlessly, you can easily see which variable combination is ideal by looking at AIC, which is an indication of model performance, bandwidth, adjusted R-squared, among other results. Now this is the fun part. So we've just run GWR on tons of combinations and found the best one. Now we've moved on to step 3, where we define our R-squared delineated neighborhoods. You can use each feature's R-squared value to create n number of neighborhoods delineated by quantile. Someone's phone is ringing. That was Javier. By quantile, equal interval, natural Jenks delineations. So automatically, all 3 regression models are run on all subsets of points within these newly defined neighborhoods. And this table shows an example of running spatial lag and spatial error on 7 neighborhoods, as well as on the global model for comparison. Looking at the AIC and log likelihood, you can see that the spatial lag outperformed spatial error with a lower AIC and a higher log likelihood. For the remaining neighborhoods, it's too close of a call to tell which is better, so further analysis is needed. Comparatively, all of the neighborhood data subsets performed better than the global model, indicating that GWR was successful in creating regionalizations and reducing those annoying spatial effects. Now that we've run OLS, error, and lag models on each neighborhood, tests for spatial autocorrelation should be done. So GWR reduced those spatial effects, and if it did that entirely, then you can just run your classic multivariate regression on that neighborhood, your OLS. Otherwise, specifications testing, such as the Lagrange multiplier, can reveal which of the 2 spatial regression models perform better. And once you have all of your models, apply that equation to each neighborhood, and you can use that to predict price. For these lower R-squared clusterings of neighborhoods, this model isn't valid, and an entirely new GWR and model calibration has to be done in order to capture those areas that were left out. But for everything else, these neighborhood-specific models can give our real estate brokers an idea if their property was over or underpriced. And this can be used to make smarter, data-driven decisions in deal-making. Let's check out an example. So this example was run using building assessment data from the New York City Department of Finance, since I can't show you RIPCO's proprietary results. And this shows a model that uses 6 predictor variables to estimate price. Using this visual, you can quickly see strength, significant level, and directionality of the predictor variables' coefficients in order to see which is more important to look for when negotiating a deal. And globally, the lag model is best. For neighborhood 1, the spatial error model was best. For the remaining neighborhoods, traditional OLS was the best. And some key takeaways. In part one, I walked you through at a high level some unique predictors that go into rent prediction. And in part two, I walked you through a logic of code that created an automated optimization strategy to get to those final neighborhood level models and explore all parameters. Thank you.